Welcome to The Explainer. Today, we're diving straight into the invisible, incredibly high-stakes world of nuclear reactor physics. You know, when we think about nuclear energy, our minds usually go straight to those massive cooling towers, the glowing blue water, and just mind-boggling amounts of power, right? But the truth is, the entire safety of this monumental system hinges on something so infinitesimally small, it almost defies logic. We're talking about the hidden hero of nuclear reactor safety, a mechanism operating on a totally microscopic level that is literally the difference between safe, sustainable power and, well, utter catastrophe. So how does less than 1% of a particle prevent a catastrophic nuclear disaster? I know, it sounds like a trick question, doesn't it? In standard engineering, if you've got a variance of less than 1%, that's usually just a margin of error. You brush it off, it's negligible. But in the realm of nuclear physics, oh no. This tiny statistical underdog is the absolute anchor of reality. But to really grasp why this fraction of a percent is the absolute most important number in a nuclear reactor, we first got to understand the terrifying environment it operates in. As you guys already know, neutron-induced fission is what drives the reactor. But the absolutely crucial metric here isn't just the sheer energy released. It's the birth rate of the very next generation of neutrons that are setting up the chain reaction. If you've got enough fuel available, those newly born neutrons fly out, they cause further fissions, and they continuously multiply the reaction. And here's where things get wild. On average, the time between two such generations of neutrons in a thermal reactor, one using uranium-235 as fuel, is a mere fraction of a millisecond. We're talking 10 to the power of -4 seconds. That is incredibly, almost unfathomably fast. Literally, before you can even blink, multiple generations of fissions have already happened. Let's translate that tiny fraction into its terrifying reality. Because the generation time is 10 to the -4 seconds, that means there are about 10,000 neutron generations every single second. 10,000! Think about what that means for a chain reaction. 10,000 cycles of multiplication happening in the time it takes you to just say the word reactor. An uncontrolled growth rate of neutrons at this speed, it would lead to an explosive, runaway spike in power. Honestly, controlling a reaction at this speed requires reflexes that just don't exist in the human body, or in any mechanical system on Earth for that matter. But here's the catch. When fission happens, it doesn't just release one type of neutron. We're actually dealing with two distinct characters here. First up, the PROMT neutrons. These guys are emitted consequent to a fission within about 10 to the -17 seconds, so blazing fast. And they pack a serious punch, with an average energy of about 2 mega-electron volts, or MeV. But second, we have the delayed neutrons. These are our sluggish latecomers. They can be emitted anywhere from a few seconds to up to a whole minute later, and they're much weaker, carrying an average energy of only a few hundred kiloelectron volts, or keV. Now, looking at the fission spectrum, there's a really interesting detail. The overwhelming majority of particles born directly from the split of the atom are these incredibly fast PROMT neutrons. They are the immediate, explosive result of the atom splitting apart, and they form the massive bulk of the neutron population inside the core. So where exactly do those sluggish, delayed neutrons come from? Well, they have a much more dramatic origin story. After fission splits the heavy nucleus into lighter products, many of these highly unstable daughter products decay via beta emission. This decay creates what we call a delayed neutron precursor. You can think of these precursors as highly unstable middlemen, like little microscopic traffic cops holding onto the neutrons just long enough to save us from prompt criticality. And the absolutely crucial takeaway here is that the delay time isn't just random. It is strictly dictated by the half-life of that specific precursor traffic cop, which is exactly why the delay can stretch out to a full minute. And that brings us to a fundamental concept in reactor physics, the delayed neutron fraction. You'll usually see this denoted by the Greek letter beta. It's a fundamental ratio. Beta is simply the ratio of delayed neutrons to the total number of fission neutrons, so the sum of the delayed plus the PROMT neutrons. It's essentially a measure of exactly how much of our neutron population is made up of these sluggish latecomers. And when you look at the raw data, it reveals how universally minuscule this portion is across different fissile nuclides. For uranium-233, it's 0.0026. For plutonium-239, it's a tiny 0.0020. And for uranium-235, the standard fuel we use in a thermal reactor, it is just 0.0065. I mean, it is incredibly small. When you actually visualize that uranium-235 fraction,
It really hammers home just how deceptively tiny it truly is. Over 99.3% of the neutrons are the blazing fast, high-energy PROMT neutrons. The delayed neutrons make up a practically microscopic sliver of the overall reality, just 0.0065. That is well under 1%.
Which naturally brings us right back to our central mystery, right? How on earth can this statistical underdog, this tiny, tiny sliver of a percent, possibly reign in the explosive speed of 10,000 PROMT neutron generations per second? There's just no way, right?
Well, the secret lies in the concept of time. Different delayed neutrons of uranium-235 have different delay times, all based on their precursors' half-lives. But when you average them all out, the average delay time for these delayed neutrons is about 13 seconds. Now, 13 seconds might not sound like a long time to you or me, but in a world where things normally happen in a 10,000th of a second, 13 seconds is an absolute eternity. It is genuinely amazing that this tiny window of time is the literal savior of nuclear safety.
And here is where the math works an absolute miracle. I like to call this the math of survival. To find the effective time between generations of neutrons, we have to calculate a weighted average of the two types. So, we take our delayed fraction, roughly 0.006, and we multiply it by its massive 13-second delay. Then, we add the PROMT fraction, roughly 0.994, multiplied by its tiny 10 to the negative 4-second delay. And check this out. Even though the PROMT neutrons make up 99.4% of the population, their time value is so infinitesimally small it virtually disappears from the equation. It's the tiny delayed fraction pulling the average up with its massive 13 seconds that completely dominates the math. The result? The effective average generation time increases dramatically to 0.078 seconds.
So, what's the punchline to all this elegant math? Because the effective time between two generations of neutrons has been stretched from a tiny fraction of a millisecond out to 0.078 seconds, the number of generations per second drops drastically. We literally plummet from a terrifying 10,000 generations per second, all the way down to a super manageable 12.8 generations per second.
The result is this absolutely crucial artificial retardation in neutron production. This reduced average neutron production rate is literally the sole physical mechanism that gives human beings, mechanical control rods, and automated safety systems the precious time they need to react, adjust, and safely control the reactor. Without this microscopic delay, thermal reactors would be fundamentally impossible to operate safely. It just wouldn't work.
It is such a brilliant quirk of nature, isn't it? A tiny, tiny fraction of a percent of neutrons arriving just a few seconds late completely tames one of the most powerful forces in the universe. It leaves us with a pretty fascinating thought to end on. In physics, where else do the smallest, seemingly insignificant microscopic fractions stand between absolute control and utter chaos? Thank you so much for joining me on this explainer. I really hope you walk away with a newfound appreciation for the incredible, hidden mechanics operating right beneath our noses. Catch you next time.